Hello, welcome to a video about Young's double-slit experiment. This was conducted by Thomas Young in the very early 1800s, and this experiment supports the wave nature of light. I'll just flag now that light is modelled as both a wave as well as a particle, so it has features and characteristics that are wave-like. It also has features and characteristics that are particle-like. This is a bit strange to think about because it's like, how could something be a particle but also how could it be a wave? Maybe a reason for that is that it could be something completely different that as humans and scientists we're yet to entirely comprehend, but at the moment we model it using both waves and particles depending on the aspect that we're specifically focusing on. So later on in this term we'll look at the particle nature of light, so I figured I'd just flag that now, just so when we do get to that stage it's not too confusing, because it's like, what the heck, we've been talking about light as a wave and now we're talking about it as a particle. So yeah, we model it as both. So I'm just going to read out the learning intentions and success criteria. Strap yourself in, there is quite a few, but they will all be covered in this video. Young's double-slit experiment can be used to demonstrate the wave behaviour of light. That's just what I mentioned before. These formulae can be used to analyse the interference pattern, where d is the distance between the slits, theta is the angular position of the maximum, the change in y or delta y is the distance between adjacent minima or maxima on the screen, and L is the slit to screen distance. We'll unpack that as this video progresses. In Stage 2 physics, you need to be able to describe how two-slit interference is produced in the laboratory using a coherent light source or using a single slit between a light source and the double slit. You need to be able to describe how diffraction of the light by the slits in a two-slit interference apparatus allows light to overlap and hence interfere. You need to be able to sketch a graph of the intensity distribution for two-slit interference of monochromatic light, considering only cases where the slit separation is much greater than the width of the slits. And you need to be able to explain the bright fringes of a two-slit interference pattern using constructive interference and the dark fringes using destructive interference. You need to be able to solve problems involving the use of these formulae, and you need to be able to determine the wavelength of monochromatic light from the measurements of the two-slit interference pattern. So sounds like heaps. We will look at all of these in this video, and hopefully by the end you'll have some idea of what these are actually asking you to do. So on this slide we've got a schematic or a diagram of Young's double-slit experiment. I'm going to outline what's happening. Feel free to annotate along with me. Everything that I'm saying is also just listed on the next slide, so it is there as well, but it could be helpful to make little notes as I'm talking through. So with Young's double-slit experiment, a coherent light source passes through a double slit to produce an interference pattern. So this light here that is approaching the double slit, this light is coherent. The monochromatic light source here for Young's double slit experiment wasn't coherent. So what had to happen in order to make this coherent was that this light source passes through a single slit, and it's that single slit that, so with the monochromatic light source, ideally, or in physics land, all of the frequencies of the light that is being emitted are the same, but they're not all travelling in the same direction. So the light is monochromatic, but it's not coherent. So all the light waves aren't travelling in the same direction and they're not in phase. In order to make them coherent, a single slit is introduced, and the light that manages to pass through that single slit is coherent, or it's more coherent than the light that is just produced by the monochromatic light source alone. So once it passes through that small slit, the light waves are all travelling essentially in the same direction, and they're travelling in phase with each other, or as close to in phase as possible. Now, if you've got a laser that produces and emits coherent light, then you can skip this section here and your laser can just shine directly through the double slit because the light is already coherent. But because back in the day for Thomas Young he didn't have access to a laser, he produced coherent light using the single slit and the monochromatic light source to convert that monochromatic light source to a more coherent light source after it passed through the slit, and then it was then able to reach the double slit with all of the waves in phase, and therefore the light being coherent. As the light waves exit each aperture, they diffract. So that means that they spread out. And it's this diffraction and interference during this diffraction that produces an interference pattern on the screen over here. So that is the screen here, and this is the pattern that it produces. So you get a combination of light and dark fringes, or bright and dark bands, and they're called fringes. Where you see the bright fringes occurring, these are called orders of maxima, and this is where constructive interference has occurred. So all of the light rays travelling to this section or this individual fringe or band, the waves have constructively interfered, so the path difference between any of the waves, the length that they've travelled, or the difference between the length that they've travelled, must be an integer number of wavelengths. Because it's an integer number of wavelengths, constructive interference occurs, so the waves, superimpose on each other. The overall displacement of the oscillations within the electromagnetic waves increase, and that corresponds with a brighter light. Conversely, where you see the dark fringes, this is where destructive interference has occurred. These are called orders of minima. For these sections, the path difference of the waves that have interacted must be an integer plus a half. So an integer plus a half number of wavelengths. So they're completely out of phase, and therefore the waves have added together, but they've cancelled each other out when they've added together. And this destructive interference, complete destructive interference, corresponds with no light. And then you've got these intermediate points where a little bit of constructive and a little bit of destructive interference may have occurred. So you get maybe something that's not quite like 100% bright, but not quite 100% dark. So it's like a gradient. And this is just everything that I've said there written out. So now this here is an example of the interference pattern that you might see on the screen in a double slit experiment. Even though we've got alternating bright and dark fringes, you might notice that the intensity of light is much greater in the middle, and then it seems to taper off towards either side. So the maximum intensity is in the centre, and then the light intensity kind of tapers off towards the other side. I'll just reiterate that each of these bright fringes must be occurring at a location where the path difference of the waves is an integer multiplied by the wavelength. And then all of the dark fringes in between must be occurring at a location where the path difference is an integer plus a half multiplied by the wavelength. And for this, m starts at 0, and it could be 1, 2, etc. For the bright fringes, m starts at 1. The reason that the intensity is the maximum in the middle is because the interference pattern intensity is modulated by the single slit diffraction. So the intensity of the light passing through each double slit isn't horizontally uniform because it's modulated by the original source, which is just a single light. So if we go back to this, so you imagine if you're shining a torch somewhere, it's going to be brightest at the center point of where you're shining the torch, and then the light will become less bright as you move away from that center point. So the exact same thing is happening here. When the light source is shining through this slit, it's going to be most intense at the center point of the light's path to these sides of the light that is diffracted through the single slit. The light will become less intense. So it's this single light source that's modulating the intensity of the fringe bands. Underneath this image, we've got a graph representing the intensity of the light bands or the light fringes, and it's the intensity is plotted on the y-axis or the vertical axis, and the distance from the central fringe is along the x-axis. So where you see a peak is where constructive interference is occurring, and that's corresponding with a bright band. Where you see a trough is where destructive interference is occurring, and that corresponds with a dark band. For the dark bands, the path difference must be an integer plus a half multiplied by the wavelength, so this rule here. And for the bright bands, the rule must be an integer multiple of the wavelength. Now we're going to have a look at the two formulae. So the first one is the path distance formula. Optical paths define the path taken by waves of light travelling to a given point. So on our diagram here, the optical paths would be R1 and R2. So these are the paths taken by the light from slit 1 and from slit 2. The path difference is the length of the difference between the optical paths for given waves or for different waves. So in this diagram here, the path difference is this length here, which is labelled sigma. I'm not going to go into the derivation in this video, maybe we can do it in class sometime, but it is on page 298 of your workbook. But basically you end up with a rule that relates the distance between the slits, the angular position of the minima and maxima, the order of the minima and maxima, and the wavelength. And that rule is this here. So d sine of the angular position of minima and maxima is equal to the order of minima and maxima multiplied by the wavelength. So this d here is this d here. The angle is this angle here. So the angle between the normal or a straight line to the screen and the line that connects the center between the slits to the point in question. M is the order of the maxima or the minima, and lambda is the wavelength. So you need to be able to use this formula and apply this formula to solve problems. The other formula that we'll look at is the fringe separation formula, and this is for maxima and minima in double-slit interference patterns produced by monochromatic light. So you have to make sure that this exact situation is the situation that you're applying this formula in. So it has to be monochromatic light, has to be a double-slit experiment, and looking at an interference pattern. We will look at diffraction patterns later on and dive a little bit deeper into diffraction, but this one is specifically for the interference pattern. This rule is how you work out the distance between two maxima or the distance between two minima. So if you've got your screen and you've got a maxima and then minima and then maximas again, I'm just going to quickly, then your y is going to be the distance between your maxima here or your bright fringe here and your maxima or bright fringe here. It's also the same, y can also be equal to the distance between your minima and your the next minima. So it's just a difference between maxima and maxima and minima and minima. So that's equal to y, that's equal to y as well, or change in y. Again, I won't go too much into the derivation of this rule, you just have to be able to use it. Maybe in class we can have a look at the derivation, but I won't do it in this video. Just to clarify, L in the rule is the length between the slits and the screen, and D is the distance between the two slits. So now I'm going to apply both of these rules. In these first two questions, we'll look at the path distance formula, and then in the next two, we'll look at the fringe separation formula. So in the first question, we've got red light that illuminates through a double slit separated by 0.125 nanometers. What is the angular position of the third order of maxima on the screen? So let's highlight what we know. We've got D, which is the separation of the double slit. We're looking for the angular position of the third order of maxima. So if we write out our rule, D sine and then angular position is equal to m multiplied by lambda, which is the wavelength. We know that m is equal to 3 because it's the third order of maxima. We know that d is equal to 0.125 by 10 to the negative 9 meters, because nanometers is the negative 10 to the negative 9. And then I've actually forgotten to include it in writing out this question, but the wavelength of red light is 633 nanometers, which is 633 by 10 to the negative 9. You don't have to remember what negative 9 meters. You don't have to remember every single colour's wavelength. I've just forgotten to include it in typing out this question, but you will be given this information. So now what we have to do is look for the angular position. So we're trying to find this here. So you can either sub all of your values in first and then rearrange. I'm going to rearrange first and then sub my values in last. I might actually even zoom in to do this, just so my writing will be a little bit neater. So this will rearrange to theta, or the angular position, is equal to inverse sine of m multiplied by lambda divided by d. Then you'll sub your values in, so you'll get inverse sine of 3, which is m, because it's the third order, and it's the maxima, and then 633 times by 10 to the negative 9. And then that will be divided by 0.125 by 10 to the minus 9, so 0.125 nanometers. All you need to do is pop that all into your calculator and you'll end up with an angular position of 0.87 degrees. So what that is saying is that from that center line, I'll just go back one, so from the center line here, this angle here is 0.87 degrees for the third order of maxima for this red light that is shining through this double slit. Another example, you've got a green laser that illuminates through a double slit separated by 0.1 millimeters. What is the wavelength of the laser light if the second order of minima are observed at an angle of 0.44 degrees from the central maxima? So let's highlight what we've already got. So green laser illuminates through a double slit experiment, or a double slit separated by 0.1 millimeters. The angle, or the angular position, is 0.44 degrees. Then we've got the second order of minima. With minima, you just have to remember a little trick. It's not as straightforward as maxima, but I'll touch on that in a second. And we are looking for the wavelength. So I'll write all of this down. I'm going to zoom in again so my writing is neat. So the wavelength is what we're looking for. D is equal to 0.1 by 10 to the negative 3 meters, so 0.1 millimeters. The angle was 0.44 degrees. And now I just want us to remember that the path difference from minima is m plus a half. And our m value is going to be whatever is in this brackets. So for the first order, that's when m is equal to 0. So the first order m value is going to be a half. So therefore, for our second order minima, the m value that we'll use in the path difference equation will be 1.5. Because it's 1 here plus a half. You only have to worry about that when you're working with minima. When it's maxima, you just plug whatever second order or third order is in. So if it's third order, it's 3. If it's second order, it's 2, and so on. With minima, it's always going to be a half less than the order that you're looking at. Now that we've done that, we can use our rule, which is d sine of the angle equals m lambda. And we are looking for the wavelength this time round, so we'll rearrange this to be d sine theta divided by m. Now I can just sub all of our values in, so I might zoom out now. We'll end up with 0.1 by 10 to the negative 3 multiplied by sine of 0.44 degrees. and then divided by 1.5, so everything divided by 1.5. Plug that into your calculator, you'll end up with a wavelength of 5.1 by 10 to the negative 7 meters. So that is the wavelength of the laser light if the second order of minima are observed at an angle of 0.44 from the central maxima. Now we'll look at the fringe separation formula. So we've got violet light, which has a wavelength of 404 nanometers, and it illuminates a double slit separated by 0.5 millimeters. Calculate the fringe separation if the screen is 1.5 meters from the slits. So our rule for fringe separation is equal to lambda multiplied by the distance between the slits in the screen divided by the distance between the two slits. We know that our double slit separation, so D, is 0.5 millimeters. The distance between the screen and the slits is 1.5 meters, and our wavelength is 404 nanometers. So I'll write all of that out. 404 nanometers is 404 by 10 to the negative 9 meters. D is 0.5 by 10 to the negative 3 meters, and L is 1.5 meters. So this D here, 0.5 by 10 to the negative 3 meters, is equal to 5 millimeters. I'm just going to draw a loop around the rule. It's a bit cluttered there, sorry about that. So now I'm just going to sub these values in. So fringe separation is equal to 404 by 10 to the negative 9 multiplied by 1.5, which is L, and then that will be divided by 0.5 by 10 to the negative 3. If you put all of those values into your calculator, your answer will end up being 1.2 by 10 to the negative 3 meters, which is the same as 1.2 millimeters. So the fringe separation between each of the maxima and each of the minima is 1.2 by 10 to the negative 3. Next example, a blue laser light illuminates a double slit separated by 0.25 millimeters, which is positioned 2.2 meters from a screen. Calculate the wavelength of the light if the fringe separation is 4.1 millimeters. So our rule again, fringe separation is equal to lambda multiplied by L divided by the distance between the two slits. Reminder, L is the distance between the slits and the screen. We are looking for the wavelength this time. We know that the distance between the slits is 0.25 by 10 to the negative 3 meters, which is equal to 0.25 millimeters. We know that L is equal to 2.2 meters, and we know that the fringe separation is 4.1 millimeters, which is equal to 4.1 by 10 to the negative 3 meters. We're looking for wavelength, so we need to rearrange this rule, and in order to make wavelength the subject, we'll need to multiply the fringe separation by D and divide it by L. Now we'll just fill in our values. So at the top we'll have 4.1 by 10 to the negative 3, and 0.25 by 10 to the negative 3. So the value for fringe separation and the value for the distance between the slits. And then underneath we'll just be dividing by 2.2, which is the distance between the slits and the screen. Pop all of that in your calculator, you'll end up with a wavelength of 4.7 by 10 to the negative 7 meters. So that is the length of the wavelength. If the double slit separation is 0.25 millimeters, the length between the slits and the screen is 2.2 meters, and the fringe separation is 4.1 millimeters. Just to finish up, I'm just going to contrast different ways of achieving the double slit or conducting the double slit experiment in the lab. So the first method uses a double slit interferometer, and in this it's like a tube, and it's basically just a setup of the double slit experiment in a tube format. So on one end of the tube you've got a monochromatic light source that might shine through a lens to focus it, and then it will be focused through the single slit. Because it's been focused through the single slit rather than being a monochromatic source with waves that are, even though they're all the same frequency or ideally the same frequency, they're not in phase. Passing them through the single slit is the adjustment or the manipulation that produces those in phase waves. So now the light source is coherent or coherent enough once it's passed through that single slit. The coherent light, so coherent and monochromatic light now, passes through a double slit. So it's like having two coherent sources, even though it's from the same source. It's just been separated via those double slits. Then the diffraction and interference will happen, so it'll produce a double slit interference pattern on a screen, and then you're able to view this through an eyepiece on the other end of the pipe. So that's how a double slit interferometer works. When you're looking through the eyepiece, there is a micrometer that includes a gauge and a crosshair, so you're able to use this to measure the fringe separation and then use your data from there to work out whatever you're determining, so maybe the wavelength of the light. Alternatively, if you've got a laser, then you can bypass the whole making a monochromatic light source coherent, because a laser is already monochromatic and coherent, so you don't need to worry about passing the light through a single slit because all the heavy lifting has already been done for you because you're using a laser. So you can just pass the laser directly through the double slit and your interference pattern will appear on the screen. If your screen is greater than a meter away from the double slit, so your L is greater than a meter, then the separation will be larger than 1 millimeter, and you can easily measure that with a ruler. Hopefully at the end of this video, those 6 success criteria don't seem as daunting and unfamiliar. We'll work on this more in class, and ideally we'll do a demonstration as well with some of our lab equipment to consolidate this topic and hopefully make ourselves more comfortable with those success criteria.